Welcome back everyone to the second video on polynomials. Today we're going to be covering some example questions involving polynomials and the theorems that we covered last time. Moving on to the next problem. If you need to read the problem, pause the video here. So to solve this problem, let's first use what we know from the remainder theorem. So if p of x has a remainder of 99 once divided by x minus 19, we can write that p of x is equal to x minus 19 times some quotient, let it be q of x, plus 99. This is what the remainder theorem gives us. And for the second part, we would have p of x is equal to x minus 99 times another quotient, let's call it r of x, plus 19. So over here, r of x isn't the remainder, just to be clear. Alright, so let's look at what we're trying to find. We're trying to find the remainder when p of x is divided by x minus 19 times x minus 99. So the divisor here is of degree 2, which means that we can expect our remainder, our answer, to be of degree 0 or 1. So with that in mind, let's take a look at this first equation. So we already have x minus 19 associated in here somewhere. But we would also like to include some form of x minus 99 in here as well, because then we can get the two things in the same place and we might be able to work something out from there. So what I'm simply going to do is plug in x is equal to 99 into this first equation. And what we're going to get is that p of 99 is equal to 80 q of 99 plus 99. But of course, p of 99 is the same thing as the remainder when p of x is divided by x minus 99. And we're given in the question that this is 19. So solving this equation, we're going to get 2 of 99 is equal to negative 1. Now what does this mean? This simply means that the remainder of q of x when divided by x minus 99 is negative 1, using the reverse of the remainder theorem. So we can write that q of x is equal to x minus 99 times some function s of x minus 1. And now we have that p of x, which is equal to x minus 19 times q of x plus 99. We can replace the q of x in here with this expression that we've worked out, right? So we can put in x minus 99 times s of x minus 1 plus 99. And this works out to be x minus 19 times x minus 99 times s of x minus x plus 118. And from here we can see that the remainder when we divide p of x by this factor here is simply this these terms over here. So our answer is negative x plus 118. Alright, so the first question says, let f of x be a third degree polynomial with these conditions. The absolute value of f of 1, 2, 3, 5, 6, and 7 are all 12. And we're asked to find the absolute value of f of 0. Now, there are some pretty interesting properties of polynomials that I want to cover. So for a 1 degree polynomial, well, that's just ax plus c. And that is just a straight line. There's nothing really interesting about it. A second degree polynomial, you might know this, it is called a parabola. So it might look like this, or it might look like that, and that is fairly simple looking as well. For a third degree polynomial, we have ax cubed plus bx squared plus cx plus d, and it can look something like this, or it might look something like this. And essentially the main points to notice here is that there are two curvatures over here. If we want to rigorously define this, we'll probably need calculus or some other form, but right here you can very easily see that a cubic function, i.e. a third degree polynomial, has a graph that has at most two curves in it. Usually it has two curves. Sometimes it doesn't curve quite up and down so much, but in general this is what a third degree polynomial looks like. Okay, with this in mind, we'll be able to tackle these absolute value signs, because it is really annoying not knowing whether it is positive 12 or negative 12 for each of these values. So to proceed, I'm going to first erase this. And I'm not going to draw the axis here because we know that a cubic would look like this or look like that. So let's first work with this first kind, where it goes from the bottom to the up as you go from left to right. So suppose that f of 1 is equal to negative 12. Is this going to work? So if f of 1 is equal to negative 12, it's down here. You might be able to see that f of 2 must be up here with positive 12. So let me take note here. And if f of 3 is negative 12, that doesn't make too much sense, because we will end up with eventually too many ups and downs for this to be a cubic function. So f of 3 has to be 12. And f of 5 is negative 12, f of 6 is negative 12, and f of 7 is 12. And if you come across this, you'll see that we can somewhat draw a curve like this through it, and we know that we have gotten what we wanted. Alright, so this is the results that we have gotten so far. Now, what do? Well, we can work from the general expression for a cubic, right? We have ax cubed plus bx squared plus cx plus d. This is the general expression for a cubic. Well, it turns out we already have 6 equations that we can work with. All that we need to do is plug 1 for each of these x's and evaluate this and set it equal to negative 12. So I'll take this for example. If we plug in 1, we're going to get a plus b plus c plus d is equal to negative 12. Simple. If we take 2, we're going to get 8a plus 4b plus 2c plus d is equal to 12. Again, very simple. And we can continue doing this for the other 4 values that we know. But we don't even need all 6, because a cubic has only 4 variables, a, b, c, and d over here. So we really only need 4 equations and not 6. And solving a system of linear equations isn't really that difficult, and I'm going to leave that to you. And eventually you're going to find that f of 0 is equal to 72. Now, you might be able to tweak these equations so that you can focus on d first. And since f of 0 is equal to the constant term, because all of the other ones involve x's and they're 0, so they don't matter. So if you can somehow find d more efficiently than solving every single variable in this equation, you might be able to get to this answer quicker. If not, solving a 4-variable system of equations while tedious, isn't a very difficult task. There is, however, a slightly better method to solve this question than we are doing right here. And what that relies on is the intuition that this function is somehow symmetric. So here we have 1, 2, 3, 4, we don't know, 5, 6, and 7. This is negative 12, and this is 12. You might be able to notice that 4 is right in the middle of all of these 6 points that we are given. And your intuition might say that the function essentially is reflective across 4. And this is a very special kind of reflection. You can actually call this function quote-unquote odd. It is odd in the sense that if you take a point, say over here, that is to the left of 4, and you take this distance between this point and 4, and you reflect it across to the opposite side, well, the value is actually flipped over. So this is a kind of mirror image that is really powerful. And essentially what it's stating is that for this function, the coefficients in front of the even powers are equal to 0. So we're going to have, if this function is equal to f of x, we're going to have f of x is equal to a times x minus 4 cubed plus b times x minus 4 squared plus c times x minus 4 plus d. And since this is an odd function, b is equal to 0 and d is equal to 0. Now you have even less variables to worry about. You only have a and c. The only thing you have to take note of course, is that the function is shifted over to 4. So if you're going to plug in the values for 1, you have to remember that it is 1 minus 4, so the thing in the bracket is actually negative 3, not 1. But that is all that you need to worry about. Now, instead of a system of 4 equations with 4 variables, you have a system of 2 equations with 2 variables. And that is so much easier to solve. And you get the answer that f of 0, the absolute value of f of 0 is equal to 72. Alright, this is it for our discussion on polynomials. Thank you very much for watching, and I'll see you next time.